So you have to consider. So this is the notation, mathematical notation for this problem. So this is general notation. It's not I'm making that for your confusion. So you have to understand what does it mean as a notation. And in the last class also I discussed about this, that one equation or one condition we can actually write in many ways. So this is one of the way. And in the last class we write another way, like this one. Initial condition is given y of 0 equal to 1. This is also means y of x naught. This x naught means 0 in here, and this 1 is actually the y naught. Okay, so y means basically in here y naught. So this is the means y of x naught equal to y naught. That means y is the y naught in here. So we can write one initial condition in many forms. Okay, so this is one of the forms.
Okay, sir.
Okay, so for solving numerical equation, differential equation using numerical solution, numerical method. So second method we have to use, that is called Euler's method. So Euler's method, we have to, this is actually something little bit different than the previous method, that is called Taylor series method. There is no series in here. So this is actually successive methods or successive iterative methods, we can say that. So basically Euler's method and Runge-Kutta method, these are called iterative method, where we have to use some iterations. That's when one process we have to iterate many times. That's when we have one process we have to repeat many times. That is called iteration. So these types of repeating methods we have to use in that Euler's method. So first of all, okay, so just give me 1 minute. I have to switch my internet connection. Okay, so we may start. So for this Euler's method, the problem description or problem specification is same as all three methods. That's when we have to solve the differential equation, and the form of the differential equation is of the form is the previous one. This is the so by this Euler's method, we have to solve this differential equation. So we have to consider this problem dy dx equal to f of xy. That's when this is actually the y prime of f of xy, and initial condition y equal to y of x not equal to 1. So that is our initial this problem description. So this problem we have to solve now by this Euler's method. So for this Euler's method, what we have to do, we have to consider there are actually two things in Euler's method we have to know. The initial method is called Euler's method, and Euler's have another method that is called Euler's modified method. So basically in this course, we are actually focusing on Euler's modified method. But Euler's modified method, it will be start from the Euler's method. This is called Euler's first approximation. And from that first approximation, we can start the Euler's modified method. So I will explain step by step, then you can understand. So first of all, we have to consider y equal to y of x is the equation, or y equal to f of xy, which is our initial equation is given in our differential equation, that is dy dx equal to f of xy. this f of xy we have to consider like as y of xy, and in that case we have to consider another term that is called h. So h will be the interval of differencing. That's when the values we have to use for Euler's method. The h is the value which is actually we can call interval of differencing. That's when we have to increase our uh, domain by h. That's when the increment of the domain, that is actually h. That's when x naught is our initial domain. That's when x1 will be the second domain, x2 is the third domain. So what will be the difference between x naught to x1 to x2, x3? Like is that interpolation method. So that is actually the domain, the range of this domain, or each of the domain has a equal interval, and this is the value is h. That's when the difference between each of the two interval or two domain is actually h. So this h we have to consider in this case. And the first Euler's approximation, I'm not actually writing or describing the whole process of getting the Euler's method. I'm just writing the final equation for the Euler's method. Okay, so how you get these things, that will be a little bit more discussion. So I'm not expressing these things because of that will actually take more time. And at this moment, it is not actually so important for you. So I'm just writing the first approximation y1 of the Euler's method. Y1 equal to y naught plus h into f of x naught y naught. So let y equal to f of x y. Also, we can write this f of x like y equal to y of x. Okay. This is actually same notation. Y equal to f of x and y equal to y of x. Same notation. Same notation. So this is our main equation, Euler's for the differential equation dy dx equal to f of xy. So this f of xy we have to consider as y, simply as y, like as f of x, and also we can consider f y of x only. Why? Because this is actually implicit function y of xy. That's when the function we are writing in implicit form. So this function basically means is actually one independent variable and one dependent variable. That's when y is the dependent and x is the independent variable in here. So if you write in an explicit form, the function will be y of x or f of x only. So this is actually the explicit form of this function of f of xy. So that is how we can write y of x. So don't be confused about this issue, because there are no two independent variables. These are actually one independent variable and one dependent variable, because of this function is implicit form. And if you write this function in explicit form, so that will be the expression y of x, or you can write f of x only. So we consider this one, and we have to consider let h be the h be the value of interval of differential. So h is means here our domain is x0, x1, x2, x3. So these are our actual domain. So what is actually domain element? So just compare with that Taylor's method series, how we done this. In this Taylor's series method, so we have to use x0 and then others values also, y0. So this is actually only we are solving for the x0. But in Euler's method, we have to solve this for many other domains like x0, x1, x2, x3, many domains. And h is the difference between these two domains. That's when each of the consecutive domains, the difference is h. So this is the equal interval of the domains. So that is actually the case. So therefore, this is we can write y1 equal to y0 into h into f of x. So y1 we can write also y of x1. So writing y of x1 equal to y. So this is our first approximate solution of the equation at x equal to x1. So as a side note, we have to write how do we find x1 in here? So we have a side note. How can we find the x0? X1. So x1 equals to x0 plus h. So that's when actually x1 minus x0 equal to h. So h is the equal interval. So if you make a list of domain x0, x1, x2, x3, so h is the difference between x0 and x1, x1 to x2, x2 to x3. So that is how we can calculate. That's when x0 will be given as an initial condition. X0 will be the given. So this is our initial condition, and y0 also given as an initial condition. These 2 points will be given. So how can you find the value of x1? We have to add the value h to the x0. And this age you have to be approximate, or this age you have to be uh, gauge or approximate. That's mean you have to consider the value of age also, and that should be very small part. So if you took the very small part of age, like that, if the value of age is very small, then you will get the more better result. So this is actually this conception is actually the same for all of the numerical methods. That's been step size. Basically, h is called the step size. That's been difference between two intervals. That is called the step size. If the step size is very small, then your result will be more accurate. So it depends on the accuracy. So how small you taking the value of h. So sometimes the h will be given in your question, or sometimes you have, if it is not given, then you have to consider a value of h. Okay, so I will discuss the value of h. How can you consider, or how can you calculate in the practical problem? Then it will be more clear. So the first approximation of the Euler method is this one. So this is actually the notation for how can we write the first approximation, that is y of x1. That's mean y1. That's mean if you put, that's mean y1, we have to find out the value. So we are finding the value of y1 or y of x1. That's mean the first approximate value. We are approximate the second value of the function, and the initial approximation already given, y of x0 equal to y0. So if you make a chart, so for as an example for your understanding, so I'll just make a table, then it will be better to understand. This one, like that, this is your domain x, and this is your domain y, and y of f of x, or whatever it is, we can say that. So if your domain, the first domain is x0, and then your first approximate value or function value is y0. If your second approximation or second domain is x1, then your second approximate function value will be y1. Okay. Similarly, you can write x2, then it will be y2, then it will be x3 and y3, and so on, many things. So these are the actually your initial, these are actually your domain, and these are the function values. So initial domain x naught is given by the problem, because this is the standard form of this problem, and initial, as an initial condition will be given. So in that initial condition, initial domain is also given x naught, and for this x naught, the initial function value for the initial domain x naught also will be given y naught. So this value will be given, these two values will be given to you. Now we have to find out the y1. That is called first approximation using the Euler's method. You have to find out the y1, and if you want to find out the y1, then you need x1, the domain of x1. So how can you form the x1? Because only y naught, x naught and y naught are given, but x1 is not given. Y1 we have to estimate. The value of y, we do not have to think about it, because we have to estimate these values y1, y2, y3. But how can we get the x1? So x1 we have to find out by the term h. So how can you make the h? We have to add h to the x naught, that will be the x1. So that's I'm writing in here, x1 equal to x naught plus h. Now the question is, what is the value of h? So value of h is a very small part. That's when we have to split our whole function, or we have to split our whole range of domain, like x naught to xn. If you write, if our domain is x naught to xn, then we have to divide x naught to xn in many pieces, and each of the interval, each of the sub interval from x naught to x1 and x1 to x2 and x2 to x3, that will be equal and very small. And this difference between, that's mean the difference between each of the consecutive domains, that is called h. And the problem is that the values of x0, x1, x3, and xn will not be given to you. And what will be the last domain of the function is also not given to you. So how can we guess the age? That is the problem. You understand the point?
Yes, sir.
That's when all of this information will not be given. Only the red part, x0, y0 will be given. So if you know the xn, then you can divide the whole interval into some intervals, and then you can calculate the value of h. But that is also not given. So what is the solution for this h? The solution for this h is that most of the cases, the value of h will be given. You understand? Most of the cases, the difference, the steps or the interval of differencing, whatever we say, the age, that will be given to you. If it is not given, then you can consider the value of age as a very small part, like 0.1, 0.1, or we can consider age equal to 0.2. That's a very small part we have to consider if it is not given. You understand the point?
Yes, sir. Understand.
Okay, so in this Euler's method, what actually we want to do? We are going to solve this differential equation. We are actually going to solve this differential equation. So this is dy dx equal to f of xy. We have to find out something y equal to something. As a solution, we have to find out y equal to something, like as the Euler's method. What we find? Y equal to something. That is actually our solution, numerical solution. Y equal to something. And same thing we have to do in here. We have to find out y equal to something as a solution of differential equation. So now in this Euler's method, we have to find out not only the y equal to something, we have to find out y1 equal to something, or y2 equal to something, or y3 equal to something. If we find out y1 equal to something, that will be called our first approximation. This is called first approximation of Euler's method. If we want to find out y2, that will be called second approximation, not first. If you find y3, that will be our third approximation. That's why we are approximating some results of this function based on the some domains will be given. So this is actually the process, but we have to solve only for the first approximation of the Euler's method. Okay, we have to find out only the first approximation by guessing or by considering the first approximate domain x1. And other terms you can find out, but this is not in our task or in our goal. This is not our goal actually for this Euler's method, because we want to find out the solution. So this is the first solution, or y1, or first approximation means first solution. That is, we have to stop. If you are more interested, then you can find out the solution for y2 or solution for y3. That's in the third domain. So this is not our necessary part of this problem. We have to stick only up to for x1 and y1. That's when we only find out the first approximate solution of the differential equation by Euler's method. That's when we only find out y1. What we find in the Euler's in the Taylor series y equal to something, that is we call in Euler's method y1 equal to something, as that means first approximate value of the Euler's method. Is it clear to everybody?
Yes, sir. Clear, sir.
Yes, sir.
Okay. So x2 y2 or x3 y3 x and y, these values are not our concern. Our concern is only x1 y1. That's when we have to find out only these two values. Basically, we have to find out y1 based on the domain x1. And how can you calculate the x1? x1 equal to x0 plus h. So x0 and y0 are already given. So we just add the small part h to the x0, that will be the x1. And this h will be given to you. Otherwise, we have to consider, or we have to guess h, the value of h, as a very small number, like that 0.1 or 0.2 or many or as much as small as possible. It's okay. So, so this is our first approximate solution. That's when our formula is y1 equal to y0 plus f of x0 y0, and x0 y0 is given. X0 y0 is given already in our initial condition, and y0 is also given. X0 is given, y0 is given. We just put these values in one, we find the y1, and that's it. This is the Euler's first approximation method. You understand?
Yes, sir.
So if I give you a differential equation, and if I say that find out the first approximation of the Euler's method, and based on this initial condition, how can you find y1? We just put this formula y1 equal to y0 plus f into x0 y0, and you know the x0 and you know the y0 value, because this is the initial condition. Put this value in the function and you will get a result, and you just add with the y0 value, and that will be our first approximation, and that is our result. So this is called the first approximation of Euler's method. Is it clear to everybody?
Yes, sir. Clear.
So this is very simple equation for the and simple solution for the differential equation, and that is why this is not a very good result or accurate result of the Euler's method. So this method, this Euler's method, is actually not appropriate or not give you the accurate value of the differential equation. So this is actually not a good method. So what we have to do, we have to use Euler's modified method. Okay? We have to use Euler's modified method. So these are actually the same thing. That's mean these have a consequence. This is not a new method. Euler's modified method is not a new method. This is just continuation of from the first approximation. Euler's modified method. So how can you start the Euler's modified method? We have to start Euler's modified method from the Euler's method. Okay, we have to start from this Euler's method. So what is the Euler's method? y1 equal to y0 plus f of x0 y0. So this is our Euler's method. So from this Euler's method, we have to start from the Euler's modified method from this Euler's method y1 equal to y0 plus f of x0 y0. And as a side note that, so y1 is a first approximation. If you want to find the second approximation like that y2, then what will be the result? Y2 will be, what will be the result? So y2 will be like this one. So that should be f of x2, and that will be y. That will be y2. If you want to find the second approximate value, that will be y1, x1, and that will be y1, and so on. If you want to find out the nth term, what will be the general form? I just write you the same thing. So that will be xn. That will be xyn minus 1. So that will be also n minus 1. That will be also n minus 1. It will be also n minus 1. So these are the successive processes.
Sir, I think after y xn, it will be yn because you wrote in the previous. Yes, sir.
Oh, that is
Yes,
y,
sir.
sorry.
Here.
That is yn, but we have to find out yn in terms of yn minus 1. So this is successive process. So we are actually strict in this form. We are not interested to find out y to yn, y to y3 up to yn. So if you want to find out, then we have to follow this method or this process, successive process. Okay. So this is called second approximation. Of the Euler's method, and that is called nth approximation. Right, is not working. Nth approximation. But we just use only in this course only the first approximation. So Euler's modified method. So same like that. First of all, we have to consider the first approximate value for the Euler's method. So what is the first approximation? So I am not writing y of x1, y of x2, y of xn. This is just for your understanding. So basically, we have to use this term. So by the notation y1, we have to understand that's means y of x1. We have to automatically understand y of x1. So this is our Euler's first approximation, y1 equal to y0 plus y of f of x0 y0. So by this method we can find out the result. But Euler's modified method, from this first approximation, we have to use a iterative process for this y1. We have to use a iterative method or successive method for y1. That means this y1 we have to use for some iterations. So what will be the iterative process? We have to write the first modified value of y1. So the first approximation modified Euler's method will be the y1 of 1 y1 of within a bracket again 1 equal to y0 plus h by 2 . So this method, Euler's modified method, and the Ranjikata method has a similarity. So if you understand this method, that will be very helpful for the next method also. It's not f of x0 y0 plus f of x1 y1. This one plus First is one. So this is the first approximation or of the Euler's method, or first iteration of the first approximation, you can say. So not in that case, we just write not first approximation, we can write first modified value. First modified value. And this y1 means actually first approximation. Y1, that's when the subscript 1, I just make it red. This is the first approximation. And the superscript as a within a bracket 1, the green color one, that is called the first modified value. Okay, this is the iteration. This is the first iteration, y1, y to the power 1, if you say that, or y superscript 1, y to the power 1 means this is the first modified value or first iterative process, first iterative value. And the second modified value, second modified value for the first approximation, not the second approximation. So we are actually finding the modified values for the first approximation y1. What will be this? Same thing, exactly the same thing. Just write in here. That's the second modified value y2, and y0 is the same always. H by 2 is same for always. F of x0, y0 is always same, and f of x1 is also same, but as a y1 we have to change. Only the value y1 we have to change. This y1 we have to replace by this value y1 of y1. This is the value we have to change. Okay, understand? The solution procedure same. So this y1 we have to change by the result of first modified value. So the first modified value y1 of 1 we have to place in here. So like as the third modified value, the same thing we have to write as a third modified value. So that will be y3, and this is just y1 of 2. So we have to use this value. We have to use this value in the second modified value. We have to use in the third modified value. Everything will be same. Is it clear?
Yes, sir. Only y1 value change, sir.
Yes, and everything will be same. And we have to continue with these things. Okay, so we can start our conversation. Okay, so hello, are you there?
Yes, sir.
Yes, sir.
Okay, so I
Yes,
just
sir.
repeat again the process. So first of all, we have to start. If you want to solve the differential equation by Euler's modified method, we have to start from the Euler's first approximation. What is the Euler's first approximation? Y1 equal to y naught plus f of x naught y naught. So we have to calculate this equation first, and x naught y naught will be the given. The point x naught y naught will be given. How? Because this is our initial condition. Y of x naught equal to y naught. So x naught and y naught, the point will be given. Okay. So these 2 points will be given. So we can easily calculate y1. So when you find y1, then you can calculate the first modified value of the approximation, this value, because in that case y0, x0, y0, these are the value we already know, and x1 and y1, so these are the value we have to calculate. So y1, this the value we have to put in here. That's when to calculate the first modified value we need y1, which is not will be given. So this y1 we can find from the first approximation. And how to find x1? X1 basically will be the given. X1 will be also given. Now, how the X1 will be given? X1 will be given because of, if you look at the problem for the Taylor series method, what is actually we have to do? We are finding the numerical solution. So numerical solution, that's mean if you, I told you that this is the, in the Euler's method, if you do not put the value of x, that's mean, that was problem. The problem was what? We solving, look at the problem. So by the initial condition, this one, we have to solve the Taylor series for x equal to 0.2. That's when we have to solve this numerically, solve the differential equation numerically for a value of x, for a specific domain. We have to solve the differential equation for a specific domain x. This x basically is the x1. This x basically will be the x1. So I told you that if you do not put the value x equal to 0.2 in our Taylor's method, then we will find the function. Then we'll find the function, and then we can put the value in here. So this is the same procedure in our Euler's modified method. But in Euler's modified method, we cannot we cannot find a function. Basically, we have to find out the numerical value directly. So this x1, basically the x equal to something will be given in your question. The x1 value will be given. That's when x1 is the estimated value. That's when we are solving the differential equation for a particular value of x. This particular value is called x1 or estimated value. You get this point? So as a side note, I can write.
Yes, sir.
Yes, sir.
X1 x1 is the estimated value of the equation. That's when this value will be given. This value also will be given. So you do not have to worry about this one. And if x1 is given, if x1 is given, then which one is left? Unknown value is age. We have to calculate the age. If x1 is given, then what will be the age? You know that
x1 minus
x1
x0.
minus x
Right, exactly right. You already know that x1 equal to x naught plus h. So from that you can find the h. X1 minus x naught, that is the h. You understand this process?
Yes, sir.
Yes, sir.
So therefore, h equal to what? H equal to this one. X naught, x1 minus x naught. That will be the h. So we get actually all the values. There is no unknown value in here. Because of initial condition x naught y naught given, and by this x naught y naught we can calculate this equation and you can find the y1. So this y1 we have to put in the first modified value of the modified Euler's method y1. And how can you calculate the x1? X1 will be already given because we have to solve this differential equation for the value of x, and this value x is the x1 in here, and we know this x1. And if the x1 is given, so we can easily calculate the h by h equal to x naught minus x1 minus x naught. So there is no unknown value in here. You get this? So now you can calculate this equation and you can find y of y1. Now the second modified value, this is just, we have to replace the same equation, we have to replace y1 by the y1 of 1. That's when the last approximate value we find, we have to put in here. In the second modified value, we have to put the first modified value. And if you want to find out the third modified value, we have to put the second modified value. And so on, we have to continue this process. So how long we have to continue? And we have to continue this iterative process until the last two are same. Okay, so this is our conclusion. This is the most important thing in this process, because you can continue this process, but when you have to stop, you have to stop if you find the last two approximate value. If you find the last two approximate values are same, that's y1 of 2 and y1 of 3 are same, then we have to stop. If they are not same, then we have to find out y1 of 4. That's mean what we have to do. So from the beginning, first of all, we have to find out y1, and we have to find out y1 of 1. And then we have to find out, we have to find out y1 of 2. Okay, so up to this y1 of 2 we must have to do. So when you find y1 of 2, then you have to compare with y1 of 1. If y1 of 1 and y1 of 2 are same, then we have to stop, and that is the result. And same means what? Because you will find the numerical values something point something, that's mean decimal point will be given. So decimal point will never be exactly same for any reason. It will be never be same. So we have to check after decimal point, maybe after decimal point, 4 decimal point will be same. That's mean after the decimal point, 4 digits are same. Then we have to stop. Or 3 digits are same. Then we have to stop. Or 5 digits are same. Then we have to stop. So this is means that continue this iterative process until the last two modified values are same for a certain decimal point. That means after decimal point, or decimal digits. That's when after decimal point, for some digits we have to compare. So that will be mentioned in your question. Then you have to correct the result up to the 4 decimal point, up to the 4 decimal digits. You get this point? Then you have to check that you have to continue this process until the 4 decimal places are same. If it is mentioned 3rd decimal point, you have to check that the 3rd decimal point will be same. Then we have to stop. Otherwise, we have to continue. You get this point?
Okay, sir. Yes, sir. Get this point.
Like that, you find y1. For example, you find y1 equal to y1 of 1. This is not y1. That's been like that. Okay, I'll give you the simple example. Okay, so this is just simple like that. You find any value, not y1. I just will tell you the process like that. A1. A1 equal to, you find 2 point, this one. Okay. And you find also A2 equal to 2.23. That's when this is actually 2 decimal points are same. In here, A1 and A2, 2, 3 and 2, 3 are same, but the rest of the results are not same. But if you find A3 equal to 2.235, some other values. Now you look at that, this for A2 and A3, 235, 235 are same. That's mean up to 3rd decimal places, they are same. So if the question is asked, you have to correct up to 3rd decimal point, then you have to stop in A3. If they are said, now you have to find out for the 4th decimal places, then you have to find out the next iteration. If the next iteration is like 2, 3, 5, 8, some other values. Now look at that, there are 2, 3, 5, 8, 2, 3, 5, 8. That's when up to 4 decimal places, they are correct. Now we can stop. This is means how can we, the iterative process, when we have to stop, when you find the last 2 approximation are same for a certain decimal digits, then we have to stop. And it will be mentioned in your question, then you have to correct up to 3rd decimal place or 4th decimal place. If it is not mentioned in your question, then you have to find out at least 3 decimal points. Keep in your mind, okay? If it is not mentioned in your question how many decimal point we have to be correct, then you have to correct at least how many? At least 3. Get this point?
Yes, sir.
So sometimes it will be mentioned, sometimes it will not be mentioned. So you have to check the question. If it is mentioned, then it's okay. If it is not mentioned, you have to correct at least 3, at least 3rd decimal point. So particular example you will see in the next class. This is up to our previous class. I'll upload this lecture sheet into the website, so you can find it here. Okay, Saiful Islam.